Dale's question. What is the condition? What is condition for this? Alright, and so the condition for this is, again, the integral from minus infinity to plus infinity of psi star psi dx equals finite. Now the comment Griffiths makes is, what if, for example, what if psi were equal to x? And then you have the integral from minus infinity to plus infinity of x squared dx. Is that finite? Alright.
No, it's linear.
Okay, so that's something cubed, a third cubed, and everything like that. So that's not going to do it. Alright? Because these things start to blow up, they run away. These functions run away.
X cubed over 3.
Alright? Yeah, so you can do it. But there's a statement in here, and I'm not going to get it precisely mathematically right. But if you have something that goes something like 1 over the square root of x and 1 over the square root of x dx. Alright? That equals the integral from minus infinity to plus infinity of dx over x. And what's the integral of that?
And log x.
That's log x, right? So that's a function that goes that's a function that looks like this. Some function that goes like, 1 over the square root of x goes like that. Okay? Now does log x, and when you integrate from minus infinity to plus infinity, equal to 0?
Doesn't it go infinite?
Okay, so I think it's infinite, right?
It never reaches 0.
What's that?
Never reaches 0.
Okay. It never reaches 0. Alright, so the area under that curve is never going to be finite. Alright, so what the statement is that, that he makes at the bottom of page 13, which Dale asked, is evidently the wave function must go to 0 faster than 1 over the square root of x. So whatever functions you do have, right, they have to go to 0 faster than 1 over the square root of x. Yeah.
Why does it matter when it goes to 0 as long as it's finite and it goes to 0?
Oh, well, that's what it doesn't. But we were trying to say, what do these things look like, or what are they?
Oh.
And so evidently they have to be functions that go to 0 faster than 1 over the square root of x.
Oh. So is that something that you could easily split whether or not something, because if something's infinite, if something has an infinite integral,
it just needs a finite integral over infinity, though.
Right. So if it's not a finite integral, then you can't normalize it.
That's it. Yeah, exactly.
But
it's not finite.
If it's something like 42, then
that's finite.
You can.
I can, and that's the whole point.
Okay.
So it has to be finite over an infinite distance. You can't just integrate it over a certain distance.
Right. You have to know the whole deal. And why is that? Because the wave function is
Infinite.
everywhere. Yeah. If it's a wave, yeah.
I mean, one quick question. How do you know it's finite? You have to solve this quadratic equation first and then...
Yeah, so these are real problems, but these are real problems that we normally don't run into. Alright? So, what we're going to do is we're going to find some nice solutions, right? We're going to find out that they're normalizable, and then we're going to use them. Alright, but there's nice work going here to prove this stuff, but I'm not going to go that route. Okay? So you need functions that go to 0. And why do they have to go to 0? Because you, at infinity, because you don't want functions that are not 0 at infinity as they go to infinity. Because then when you integrate them, you come up to be a finite number, an infinite number as you go up to infinity. And that's the whole story. Okay? So, here's the deal. Here's the last deal on this stuff. Is that the last connection that I want to do is the following, is that square integral solutions to Schrodinger's equation form a complete basis set in function space. Okay, so what does that mean?
Like, you know, the range of numbers it deals with.
Okay, kinda. I mean, I keep forgetting that you guys might not have heard this. But here's a primer. In vector space, I hat and j hat, what do I usually? A span 2D vector space. So for example, here's I hat and here's j hat. Oh, sorry, yeah, j hat. If I have any vector f, a two-dimensional vector, f can equal f of x in the I hat plus f of y in the j hat. Okay? So how many basis vectors do I need in two-dimensional space to completely describe all vectors that may live in that space? 2. All right?
So this covers all the functions for the...
So now, imagine a function of x. Here's a f of x, and here's x. All right? Would I say they form a complete basis set in function space? In other words, they span all the function space. All right? So, for example, Fourier series. Everybody's heard of Fourier series and done a little with Fourier series?
Right, you make function space.
Okay, Fourier series of sines and cosines.
Mhm.
Infinite number of sines and cosines of different frequencies. Right? So, for example, here's cosine of 1. Here's cosine of 1x. Here's cosine of 2x. It's cosine 2x. And cosine 3x. Right? 4x, 5x, 6x, 7x, 9x. And when I get to, 11, what happens to the board?
Completely black.
It's completely filled in. Right?
Which means that all those points are plotted to or mapped to.
So it means I can get to all of, what it means is that if I had some function that looked like this,
That's a little too normal, make it a little less.
okay, could I rebuild the blue in terms of some of these cosines?
Yes.
Yeah.
Yes. Okay? Everybody got that? That's a deep idea from linear algebra. All right? Which was probably never presented that way to you in linear algebra. All right? About function spaces and stuff like that. But what is the dimension? So the dimensions of this space is 2D. Right? What are the dimensions of the... So I needed 2 basis vectors here. How many basis vectors or basis functions do I need here in function space?
Sine and cosine?
I need an infinite number of them. Cosine 1, cosine 2, cosine, all the way out to infinity.
Yeah.
And by the way, can I get to a point up here? Sure, I can. Just about put it... I have 3 in front of this, and it makes it 3 higher.
Change the constant in front of the...
Yeah, but see what happens is these basis functions, the infinite number of them, span all of function space.
Right, because those just go between 0 and 1 now, but you could put a constant in front of it.
I can get anywhere,
to get-
and that's how Fourier series and Fourier analysis works, guys. That's Fourier analysis,
It
right?
can't be hyperbolic, then it has to be repeatable.
Say that again.
It can't be hyperbolic, it has to be like
Repeatable? For Fourier series, yes.
Okay.
But there are these things called Fourier integrals, and they don't have to be. But that's a
Okay.
subtle point, yeah. Yeah, there's different types of spaces. So there's different type of infinities, all right? Fourier series is a denumerably infinite series, cosine 1, cosine 2, cosine 3, cosine 4, right? But you can also have an infinite and a continuously infinite, where, you know, it's cosine 0.1, cosine 0.2, cosine 0.3, stuff like that. All right, but I don't want to talk too much about that. Okay, so the big scoop is square integrable solutions of Schrodinger's equations form a complete basis set in function space.
Those are all possible functions for.
Okay? Therefore, a couple things, all right? Therefore, the solutions to Schrodinger's equations are like I hats and j hats. And if you find a nice clean solution to Schrodinger's equation and a nice easy I hats and j hats, can I build a more complicated solution out of those easy ones?
Yes.
Yeah. So what ultimately I'm going to do is I'm going to look for the easiest case solution to Schrodinger's equation, get my I hats and j hats, and then later on, to solve complicated problems, simply sum my I hats and j hats to get solutions to harder problems.
It's